Stop, the universe is missing 2,000 galaxies. The radio dish was pointed straight at Boötes, but the headphones were strangely quiet. It wasn't a total silence, but the sound felt thinner and emptier, almost like someone had turned the volume down on the entire sky. On the monitor, the source counts kept ticking lower than any of the control fields. Where the team expected to see 2,000 galaxies, only a few lonely dots blinked back from the darkness. The technician muttered something about checking the gain, but even after they confirmed the equipment held steady, the gap remained. The astronomers stared at a 330 million light-year hole in the universe and admitted that it just couldn't be right. Here's the thing. If the map is missing that much material, maybe the map is fine and reality itself has a hole in it. And that's the riddle that's been bothering people ever since. What is the Boötes Void? Let's start with the facts, plain and simple. If you look toward the constellation Boötes, you'll find a massive, roughly spherical region of space about 330 million light-years across that has far fewer galaxies than it should. Astronomers call this place the Boötes Void. To visualize it, you have to picture the cosmic web, which is a massive network of filaments and sheets of galaxies that looks a lot like a three-dimensional sponge. Now, imagine someone reached out and punched a softball-sized bubble right into the middle of that sponge. And that empty bubble is exactly what Boötes looks like. You might wonder how anyone even noticed a hole that big in the first place. Back in the late 1970s and early 80s, research teams were running redshift surveys where they would point a telescope, take spectra, and measure how fast galaxies were moving away to build a 3D map. In certain directions near Boötes, the pencil beams kept returning nothing. And you know what? Astronomers absolutely hate finding nothing. They pushed deeper and widened the beams to find more data, but they just hit more nothing until they finally started to pick up a rim, which was a kind of wall of galaxies skirting a massive emptiness. Get this, if you take a volume of space that big in a normal part of the universe, you'd expect to find on the order of 2,000 galaxies bright enough to show up in those surveys. Inside the Boötes Void, early counts found only about 60 or so, and while later work nudged that number a bit, it's still a massive canyon of underdensity. It isn't completely empty, but the population is shockingly low. Now, we know the universe isn't perfectly smooth. After the Big Bang, tiny ripples in density grew under the pull of gravity, and matter flowed into filaments and nodes while leaving behind these voids. These lower density regions are actually normal, and they usually expand faster than their surroundings. But typical cosmic voids are tens of millions of light-years across, not hundreds. Most of them are irregular and live tucked between walls of matter, but Boötes is oversized, surprisingly round, and incredibly deep. And that combination is what makes people squint. So what exactly do we mean by round in this context? When you slice the sky and stack the redshifts together, Boötes shows up as a broad, near-spherical patch where things are missing. The boundaries aren't perfect because they're a bit lumpy, but you don't see a long, skinny tunnel or some kind of layered gap. You get something that reads like a giant bubble in both projection and depth, and that's weird because the cosmic web is usually made of sharp elbows and flat sheets rather than clean balloons. Let's put some real numbers to this deficit to show the scale. If the average galaxy density in a normal volume is n, this void comes in at something like a few % of n for bright galaxies, though that depends on which catalog you use. That's where that back-of-the-envelope idea of missing 2,000 galaxies comes from. It isn't an exact invoice of every star, but it's an order of magnitude gut check that tells us we should see thousands when we only see dozens. Why does this matter beyond being a cool trivia fact? It matters because our models of how the universe formed, the way dark matter clumps and gas cools, predict a specific distribution of void sizes. If Boötes sits way out in the tail of that distribution, then maybe it's just a rare event. But if it's too big or too clean to be a statistical fluke, then our physics might be missing something huge. Hold on, because we have to consider that biases are real in science. Our own Milky Way blocks parts of the sky with its own dust and stars, which is a problem called the zone of avoidance. But Boötes isn't in that belt, and astronomers have checked the area in multiple wavelengths like optical, infrared, and radio. Dust can hide light, but radio waves sail right through the debris, and the source count still stayed incredibly low. That's why people take this void seriously, because it shows up again and again, no matter what tools we use to look at it. So the central question lands right here. Is the Boötes Void just the extreme end of a natural process, where an underdense region got an early start and kept expanding? Or are we just fooling ourselves with the way we pick and count galaxies? Or, and this is the uncomfortable door number 3, is there some other process that wiped out or prevented normal galaxy growth on a colossal scale? The stakes for this answer aren't small at all. Dark matter models tell us exactly how clumps form from tiny seeds, and if those rules can make a bubble this big, then we learn just how wild the universe can get. If they can't, we're talking about changing the nature of dark matter or revisiting how black holes heat up and clear out gas. Even the way we measure cosmic expansion could be nudged by the fact that we are looking across these massive underdensities. There is a human stake to this story as well. Imagine spending years of your life building a map only to realize there's a giant bite taken out of it. You would triple-check the instrument and swap telescopes, and you'd even ask the colleagues you argued with at the last conference to take a look. The hole doesn't go away, and that's the emotional core here, because scientists don't chase gaps for the drama. They chase them because gaps are where reality tells them to try again. Here's where it gets really interesting. The first radio passes over the Boötes region didn't just fail to find bright galaxies, but they actually reported fewer faint radio sources than other patches of the sky. You'd expect the background to even out when you add up all the tiny emitters like distant active galaxies and star-forming dwarfs. Instead, the radio sky itself seemed to thin out, and that's a clue that puts real pressure on the simple stories. Because if there's less radio noise coming from that direction, this isn't just an optical trick, and the underdensity might cut across populations we thought would smooth everything out. So that's our setup. A round, giant, underdense bubble sitting right where the cosmic web should be busy. It's a discovery that started as a stubborn bit of nothing and grew into a structured absence that is big enough to make any statistician sweat. From here, we have to start testing the stories, whether it's a natural void, hidden matter, or something much stranger, to see which one breaks first. How we found it, the surveys that hit a wall. To understand how we actually stumbled onto this hole, you have to look back at the early days when astronomers were counting galaxies one by one. They weren't actually hunting for a giant void at the time, but were instead trying to build a 3D map of the universe. The way these optical redshift surveys worked was pretty straightforward. You pick targets from photographic plates, feed them into a spectrograph to read their distance, and then stack those distances into a 3-dimensional slice of space. In the direction of the Boötes constellation, those stacks kept coming back incredibly thin. It wasn't that the images were blank. There were plenty of candidate galaxies to look at. But when the teams checked for actual objects at the right depths, the galaxies simply weren't where they were supposed to be. Slice after slice, a massive gap started to grow in the data. Here's the thing with optical work. Selection bias is always waiting to bite you. If you only choose the brightest galaxies, you end up biased toward the easy targets, and if you rely too much on color, you might accidentally skip over the dusty or weird ones. Because of that, the pushback from the scientific community came fast. Critics argued that maybe the target list was skewed or the exposure times were just too short to see anything. The teams adjusted their methods by using deeper integrations and different color cuts across wider fields, but the results didn't change. Unknown to them, other groups across town were using their own fiber-fed spectrographs to look at the same spot, and they found the exact same underdensity at the same depth. While all of that was happening, radio astronomers stepped in with a much blunter question. They figured if dust or the glare of nearby stars was hiding something, radio waves wouldn't care at all. They pointed their massive dishes and arrays at the patch, looking for the steady hiss of active galactic nuclei and starburst galaxies that usually light up at centimeter wavelengths. But get this, the counts didn't fill in. You normally expect a specific number of faint radio points in any random square of the sky, but in the Boötes patch, the histogram just sagged. Even after they rechecked their sensitivity maps and cleaned up the data, the deficit held firm. Infrared surveys eventually passed the same test with the same eerie results. If this whole thing had been a trick of old stars swamping out blue light, the mid-infrared should have made those dusty galaxies pop right out. Instead, the surveys that swept the sky at those wavelengths still saw a total desert, save for a few oases on the rim and a handful of lonely galaxies crossing the interior. Even ultraviolet light, which is great at finding young and hot star formation, didn't suddenly reveal some hidden cosmic city. This emptiness wasn't just some single-band illusion. It was looking more real by the minute. People eventually brought up the zone of avoidance because that's the classic gotcha in astronomy. Our own galaxy's disk throws so much dust and stars across our field of view that it erases background galaxies unless you switch to radio or infrared. However, Boötes sits well clear of that messy belt. The star counts are low in that direction, the extinction maps are boring, and the coordinates don't line up with any of the crowded lanes of the Milky Way. It's definitely not our own backyard blocking the shot, so the gap is a real sky feature, not a foreground trick. Data integrity soon became an absolute obsession for the researchers involved. Since catalogs are stitched together from many different nights and detectors, tiny choices in how you flag cosmic rays or set a detection threshold can accidentally carve out artificial holes. To fix this, teams ran null tests where they rotated the sky patch or injected fake galaxies into the raw images to see if the pipeline could still find them. They even masked out bright stars and repeated the entire process from scratch. No matter how hard they tried to break the data, the Boötes hole refused to go away. Reproducibility is the only thing that helps scientists sleep at night, and in this case, the evidence took decades to solidify. The early plates from the 1980s only hinted at a gap, but the multiplex spectrographs of the 90s finally firmed up the discovery. By the time 2000 surveys with automated pipelines arrived, the hole had become boring in the best way possible. Different telescopes and different teams across both hemispheres kept hitting the same wall at the same coordinates. If this were a glitch, it would have to be the most consistent and elaborate glitch in the entire history of sky surveys. Meanwhile, something else was showing up in the radio numbers. When you average the radio sky over thousands of faint sources, the data usually smooths out, which is why radio astronomers love deep fields for their statistical power. In the Boötes region, the faint end of the population looked completely drained. They cross-matched every catalog they had to weed out duplicates and checked their completeness against the noise floor, but the bow and the source count stayed put. This suggests the underdensity isn't just about losing a few bright beacons. The void actually bleeds into the background population of the universe itself. What nobody knew at the time was whether special pockets of space elsewhere could fake this same look. To find out, they pulled comparison patches of sky that matched the same galactic latitude and used similar observing strategies. Those control fields showed exactly what you'd expect for a typical region of the cosmic web, filled with filaments, clumps, and plenty of low-level radio hash. Boötes remained the total outlier. There's still a bit of humility in the margins of this research. It's possible that diffuse, ghostly galaxies are slipping under the detection floor because of surface brightness limits. The count of dwarf galaxies per unit of volume also has some lingering uncertainties, but those are small, nibbling questions compared to the massive gap we're seeing. The bite taken out of Boötes is too clean and too broad, and it shows up in different methods that shouldn't share the same biases. If it's an illusion, it's a massive conspiracy across wavelengths and decades. But if it's real, the story of how it formed has to be much stranger than we thought. The cosmic web versus a spherical nothing. To understand why this hole makes people so nervous, you have to zoom out and look at the big picture. The early universe wasn't perfectly smooth, as it started with tiny ripples in density that were stretched out by inflation. Gravity eventually grabbed those ripples, and over billions of years, matter flowed from the low spots to the high spots. This created long filaments and thick walls, leaving behind the underdense basins we now call voids. That's the cosmic web. It's a tangled, knotted sponge rather than a neat grid. Voids are a standard part of the cosmic deal. They aren't totally empty, but they are very light on matter, meaning galaxies inside them are rare, small, and faint. A typical void might run about 20 to 50 million light-years across. Occasionally, bigger ones show up when smaller voids merge together like bubbles in a sink full of foam. These are usually lopsided and snake between sheets of galaxies, with edges cluttered by the walls where matter finally settled. So why is Boötes such a massive problem for this model? When you map it out, the whole region looks like a bulbous cavity hundreds of millions of light-years across with a fairly smooth interior. It isn't a perfect sphere, but it feels round in a way the cosmic web rarely allows at that kind of scale. You expect voids to look like crumpled, irregular rooms between walls, not like one giant balloon that was blown up inside the lattice. Here's the thing. Our computer simulations of the universe do make voids. If you feed in a starting spectrum of ripples and let dark matter run forward under gravity, you get plenty of empty spaces. But to get something the size and depth of Boötes, you usually need a very specific set of circumstances. You either need a chain of smaller voids so perfectly aligned that they fake a sphere, or you need an initial underdensity that was exceptionally deep right after the Big Bang. Both are possible, but the first is a lucky trick of perspective, and the second is a rare roll of the cosmic dice. Let's talk about the actual depth of this thing. Underdensity is measured as a fraction of the average matter density in the universe. A mild void might sit at about 20% below average, while the deeper ones hit 50% or more. Boötes, at least for the bright galaxies we can see, punches far below those numbers. That doesn't necessarily mean the total mass deficit is that extreme, because galaxies are biased tracers of matter. In low-density regions, galaxy formation is suppressed, so the lack of light can make the whole look even more empty than it actually is. Still, even after you account for that bias, the gap looks incredibly hefty. The roundness of the hole is the second major point of tension. Gravity and cosmic expansion usually make voids more spherical over time as they empty out, but the surroundings usually fight that process. Nearby filaments and walls of matter tug on the voids and distort them into weird shapes. A monster cavity staying relatively round suggests it either had plenty of room to grow without neighbors, or it grew very fast from a uniform low spot. Simulations show you can get that result, but it's a 1% event that rarely looks this clean. Then you have to consider the timing. The universe has had about 13 billion years since the first atoms formed, and void growth is a slow process of matter draining to the edges. To empty out a region this big, you need the clock, the initial conditions, and the neighboring galaxies to all cooperate perfectly. When teams run large simulations with standard dark matter, they do find big voids, but Boötes always sits at the very edge of the distribution. It's the kind of outlier that makes you wonder if you're missing a piece of the puzzle. Now you might say that rare doesn't mean impossible, and you'd be right. The natural void camp leans heavily on that logic. If you stack enough cosmic volumes together, you're eventually going to draw a long straw. To be fair, the rim of Boötes does look like a place where matter piled up into clusters and walls, which is exactly what physics predicts. The handful of small, odd galaxies inside also fits the story that galaxy formation just limps along in these underdense zones. But that's where it gets really interesting. If Boötes is just the extreme end of a known pattern, then other statistics should agree with it. We should see cousin voids nearby that are trending toward that size, and the neighboring filaments should look stretched by the hole's growth. We should even see a weak integrated Sachs, Wolf imprint on the cosmic microwave background as photons cross the underdensity. People have looked for these signs, and while they find hints consistent with a real underdensity, they haven't found a dramatic, smoking gun that explains everything perfectly. The last piece of the puzzle is the centering. Our surveys found a cavity whose center sits almost squarely in the middle of a mapped region. That's partly a selection effect. You only find what you're looking at, but it still raises an eyebrow. If giant, round voids are really that rare, catching one so well-framed feels like an incredible stroke of luck. Luck happens in science, but when you get enough of these lucky alignments, you have to ask if the model itself needs a nudge. That's where the tension stands today. We have a theory that expects a knotted web of small, messy voids, but we're staring at a hole that's too big and too bubble-like for comfort. The natural story can be stretched to fit the data, but it's stretched to the breaking point. To see if that stretch finally snaps, we have to look at the more extreme hypotheses and see if their math can actually carry the weight of what we're seeing. Theory Path 1, an extreme natural void.